Evening, mother lovers. This is everything you need to know about stats. So let's go. We're going to split into two. We got foundations, and then we've also got the kind of higher tier of stuff. What's in the foundations is going to be everything from GCSE. A lot of it is from GCSE, and the rest of it is all kind of simple. It's a lot of facts, a lot of things to just remember, some definitions. Topics in there then is all the sampling stuff. It's going to be everything about kind of the basics of stats, like mean, the standard deviation, interquartile range, those sorts of things. We'll also have the graphs on that side. So these bits will be nice and simple. Shouldn't take us too long to go through most of those. It should be that you know most of it, and the rest of it is kind of common sense. On the other side then, what we're going to have, they're the bits that are all kind of brand new. So we're looking at correlation. We're looking at all the probability stuff. We're looking at the distributions. And we're looking at hypothesis testing. So 7 things altogether. One thing we're not looking at is the large data set. Just find yourself a summary online. I don't know much about it. It's a very silly thing, I think, that you have to memorize this thing. So let's get going. First thing then, the sampling. We need to know some definitions. So let's have a look at a few of those. So some definitions. We have the idea of a sample, obviously, and a census. They are effectively the same thing. The only difference is going to be how many people you ask. So here we ask everyone in a census, and in a sample, it's not everyone. That's the only difference between the two. What we're doing inside these to actually get the answers can be in both. Like, it doesn't matter which one you're doing, whether it's going to be like a quota or whether it's going to be opportunity. You can do that to get both of these. But if you ask every single person, every single member of your population, then you're going to get their census. If you don't, it's a sample. So yeah, population is a good thing to think of. That's going to be on the census side. And we're going to have a sampling frame on the sample side. So like a sampling frame is a subset of the population. This could be everyone in the UK. This could be every woman in the UK. It's going to be a smaller group, but every single member is part of the population. And then within those, we're going to have sampling units. They work on both sides. They're the actual people you're asking. So this is the idea of like the actual everyone in the country, and then this is just you yourself. So like what people or what items or elements make up the set of the population. Are we looking at all the people? Are we looking at every car? That sort of stuff. That's going to be the individual cars or individual people. So that's good. Another thing to think about is going to be the types of data we can get. So either we're going to get continuous or we're going to get discrete. The difference is basically, can you get more accurate? So for continuous, you can always get more accurate. Think about measuring a distance. Oh, that's 18 miles away. Actually, it's 18.5. Actually, it's 18.56. Actually, it's 18.564. And you can always get more and more precise with a continuous. There's no smallest resolution. You could stop at the millimeters, but we could just keep going, do you know what I mean, to nanometers and femtometers and getting smaller and smaller and smaller. The other side, discrete, there's a fixed number of outcomes. And you can think the other side then, there's infinite outcomes. It could be that you don't know it. It could be that we actually don't know how many there are. And it might be, oh, how many cars are going to pass by this hour? You might not have an upper bound. But there's not going to be an infinite amount in terms of, like, you couldn't get 0.4. You know, at some point there will be a max amount that's theoretically possible to get on that road. You think a car's 2 meters long. If the road's only 100 meters long, you can 50 at a time. Times that by how fast they're going. That's the max number you could get. So we're able to set like a limit to how many possible outcomes there can be. Whereas continuous, there's an infinite number of outcomes available to you. The other side of that then is going to be whether we're talking about numbers. Are we talking about quantitative data, or are we talking about words? We're talking about qualitative data. I always just look at the kind of fourth letter. So you've got L for language, and you have N for numbers. And it is as simple as that, basically. Like, is the thing you're talking about numbers? Can we use it to compare them? Is one bigger than the other one? Do you mean, can we order them? this stuff is basically stuff we can't order. If I say ask what's your favorite color, you can't really put an order to that. You could ask like what's your favorite cat, what type of cat. No real ordering to those sort of things. But we can ask like how many pets do you have? That can have an ordering because 4 is more than 3. So that's the basic start of it. When we look at then the different types of sampling, what methods can we actually use to get these samples? So the types. And again, these get split into different subsections. So we have the random ones and the non-random. And they're basically the methods we're going to use to ensure that we do fill our sampling frame and ensuring that they are the correct sampling units. So types of random ones, we can just have simple random, where there's kind of no method. you like pick things out of a hat. Do you know what I mean? That's the only way you're going to get them. We get every single member of the population, and we're just going to pick out, say, 100 of them from a hat and ask those 100 people. How we actually ask them from there, we don't care about. We're just thinking about the method that we use to select who is in our sample. We don't care how we're actually asking them at this stage, just how are we selecting them. Another type of random sampling then is going to be the stratified. So stratified, the word in there is strata. Strata just means group. It's just a fancy, I think, like Latin word for group. So effectively, we've split them up into different groups. They have to be mutually exclusive. We will talk more about that later on, but effectively, it means that you cannot be in 2 groups at once. So not in 2 groups. So that determines like the ways you can split the population up, like the different strata you're allowed to have. So you could split people by age, you can split people by gender, by race, by birthplace, but you cannot split them kind of at 2 of those categories at the same time. Because if I could be in the category of like, oh, I'm under 40 and I'm born in the UK, I'm in 2 groups. That's not allowed. We have to have every single person is in exactly 1 group and no more than 1 group. So that's going to be strata. Why they're different than quota is simply the way that we're then filling these later on. So the strata, the stratified, we're doing that randomly. We know who should be in which sample. Like if I was to ask the random person in the population or like select them from my population, I know which group they go into. But how I actually put them into those groups is up to something else, like simple random or something else that we're going to do. Whereas on the quota side, it's going to be a different way where it's kind of non-random, and we're going to end up just trying to fill the groups, and we're going to keep asking everyone until you've just filled the group. And if you ask someone and their group is full, we just ignore what they've said. We just don't listen to them because you were too late. It's first come, first serve to get into your group. So this is the same thing. It's going to be grouped again, but we're doing it non-randomly. So we're going to go and fill our quotas. Fill quota. How do we know how big our quota is going to be? Well, if I know in my population I had 100 people, say, and 20 of them were born in Wales, I need to make sure that 20% of my sample are also born in Wales if I've split the groups up to be like birthplace, where you're born, something like that. So we want the same proportion. The sample size, the sample proportions, so sample proportions are equal to the population proportions. This is what they will call representative. Representative. If you don't have your sample being representative of your population, your sample may well have not been done. Because there's no point me trying to find out information about people in your school if I'm asking the old ladies at the bus stop, because they don't know. They don't have the same information as you, not the same viewpoints, not the same views. So you're not going to get data that is useful, because the whole point of these things is to take, we're going to look at a very small set, think, okay, you guys think this, so we can probably think that everyone else thinks roughly the same stuff. And the more people we ask, the more confident we are in saying that, okay, this group think this, so everyone probably thinks something similar to that. That's the whole goal of what we're doing with these samples and surveys and censuses and everything like that. The other types we have then, what needs to go in as well, we're going to have systematic on this side. Systematic is quite simple. We're going to order them, and then we're going to make sure that we have every like 10th person, say. So we order and then pick every nth. I think they do k, so pick every nth person, or every kth person. That doesn't mean that you're going to order them. Say we had 100 people. You're not going to pick number 1, 10, or 1, 11, 21, etc. It might be you pick 6, 16, 26, 36. But the spacing is always 10, or whatever number you need to pick it from. But the starting value doesn't have to be the first one. It could be some like 10th one or another value. How we work out the k, you're going to take your pop size, your population size, and divide it by your sample size. So k is basically going to be how many people, out of how many people get asked, or like 1 out of every k people get asked. So if k is 20, 1 out of every 20 people are going to be asked, because you need every 20th person in that case. I think that's it for sampling. Let me double check, but I think that's all good. Opportunity, you just wait. You just do like what's easiest. Do you know what I mean? I'm gonna stand outside and just ask people. Opportunity, if I could spell. Opportunity. Yeah, you're just gonna wait by do whatever's easiest. I'm gonna shout at my window and ask people, "Oi, what do you think?" And then just fill in my survey from that. Easiest. That's that's a good example of it. Do you know what I mean? What's the easiest thing you can do? The stuff you look at then is going to be like pros and cons. Why are these good? Why are these bad? Just have some common sense. You've lived in the world for a long time. If I want to do a census and ask every single person, that's a bit of a ball ache, isn't it? If I've got to ask everyone in the country a question, there's what, 70 million of us, it's going to take a while, isn't it? It's going to take a bit of a while. Much harder than asking like 1,000. So, downsides of a census just takes bloody ages. It's going to be expensive too to ask everyone. So samples, benefits is cheaper, quicker, easier. Looking at these as well, opportunity, easy, cheap, quick, simple random, again, easy, no faff. This is going to be hard. You have to decide your groups. Make sure that you actually put all the people into the correct groups, know all the information about them beforehand so that you can put them into the groups. So that works with every type of groups. And again, it might be more expensive to do that. It's going to take a little bit longer. So just think common sense. What's going to be easy? What's going to be hard? What's going to be cheap? What's going to be expensive? They're the bits you want to consider. So it's going to be what's easy and hard, cheap and expensive, and then quick and slow. Really, everything comes down to that. Done it. It's the world. Everything comes down to, can we afford to do it? The more people that you sample, the better results you will get, but the more money it will cost. Hence why sometimes you want a really good sample, but to get the quality of a sample, you have to kind of let down the quality of your extraction of the data. So we want to get a big amount of data, so we're going to do a very simple survey to get such a large data. Or we want to get very precise data on certain groups and make sure that we're matching it there. But that's going to be more expensive to do. So we'll do a smaller sample. So you're always balancing the kind of quality that you want to get out of your survey and the price that it's going to cost. Because at the end of the day, everything comes down to, will someone pay me to do this? And if the answer is no, then you're not going to do your survey. So that's sampling. Hopefully not too bad. Should be nice and straightforward. Let's go to the next bits. So, intro to stats. This is, you'll probably know most of this. It's a lot of GCSE. So we're looking at what is a mean. Mean is just where the average, yeah, where everything's going to be. If I did this 1,000 times, what do I think will happen? What was my guess that would happen? So we write that X bar. The bar is always going to mean, the mean. The mean average will just have a bar on top of it. Anytime you see anything really with a bar at the top, especially in stats, will mean average of that thing and mean average. So how do we work that out? We add everything up and divide by how many things there were. No faffs, no difference, all the same as when you're at school. Only difference is going to be that we might now have group data, which I think you do see at school as well. How do we do that? We do this little column, don't we, where we times the midpoint of our group by the frequency of our group. What is that doing? Well, if I have a group that say I can run 100 meters in 11 to 12 seconds, and we had 20 people in there, the average of that would be 11.5. So we have 20 people between 11 and 12 seconds. So yeah, the average will be 11.5. So what this is working out for every single group is how long did that group take in total. So if we do the 20 times 11.5, we get 230. So 20 times 11.5 equals 230. So collectively, the 20 people in that group took 230 seconds to run the 100-meter races. And when you do the mean, you want to work out the total time that everyone took together. So this is just how we do it in groups. You work out the total time in that group, and then you add all of those things up. And you're going to divide by, again, how many people there are. So both rows on the bottom are how many people. The number of people. It should really be sampling units. I'm just going to keep saying people for like sampling units all the way through. Imagine every single thing is just about people. Do you know what I mean? But both of these are just referring to the number of people. This looks strange, but it's just adding the frequencies. It's the result of the cumulative frequency of your entire sample. So every single person that you ask. So those bits you've probably seen before. Nothing too fancy there. One thing to think about is now we might have linear operations on these things. So in general, we're talking about some distribution that we have, and we're thinking about where is the peak of this distribution. No, we're not. That's the median. What we're thinking about is like just the middle of our distribution. That's going to be x bar. And as we do linear operations on that, firstly, what do I mean by those is when we take something, instead of looking at x, we're going to go to like ax plus b. So we've done something linear to it. We've operated on it in a linear fashion. We've multiplied by so much and added so much to it. But what do these things do? Well, the multiplication side is just going to expand it out. We're going to stretch this thing out. Does that change the mean? No. Yes, sorry, but it doesn't change the kind of spread of it. But when we think about the mean, if we just doubled every value, that would double the mean too. If I tripled it, I triple it. If I quadruple all these, I quadruple the mean too. So whatever we do to every value, we're going to do that to the mean as well. Same thing happens here. If I was doing every single number and I just added 10 to them, my mean becomes 10 times bigger. So what we see, if we think about having some kind of function that takes in our set of data, this is your data set, this is every value you got out. Normally, it would just give us the mean. But let's say instead of having that data set, let's just move over a little bit, we've taken it and we've done the operation to it. We've times everything by so much and we've added so much to everything. What we can do is take those bits out of this function. It would just end up having the normal mean that was produced. We would times that by that a number and we would add the b onto it. So what we see, it's basically a transformation. Think about transformations from GCSE, it's the same thing. Exactly the same thing is happening. If you plug in this sort of stuff, you end up transforming your graph. And we're going to see that we can effectively add b to it to move it this way. And if we were to stretch it, it would move it that way as well. Might be left if it's negative, do you know what I mean? The same sort of ideas. Similar thing happens then with the variance. So let's have a look firstly at the variance formula. We have two of them. There's one you'll probably use, and then there's one that kind of is the actual definition of it. So we'll look at both. We're talking about variance here. Variance. This is always going to have sigma squared. Everything we're saying is still true for the standard deviation, but often it's going to be the square root. Anything that is different, I will mention, like anything that's slightly different, but most things will work exactly the same way. Or what you do is just always work with variance, and if you ever want standard deviation, you just square root it at the end. So the formula then, what is it actually doing? Well, we're basically asking the question, if I take my data points, so I have some distribution, and again, I know where the mean is, but we could think about having, say, a data point over here. We want to find out, of all these data points that we have, height here means nothing, by the way, I'm just going to fill in the space. How far away are they on average to this thing? What's the spread of our data? How fat is this? It's a measure of how many C's are in the thickness of our distribution. Do we have a distribution that has only got one C? No. Do we have one with a million C's? Maybe. Let's find out. But this is the study of that and trying to measure it and see how thick is our distribution. You could do this in a lot of ways. You could just measure these distances. That would be called like the absolute variance, I think. I don't know if you've got a special name, but it's not something you learn about. We end up doing the square of it. So we're going to go through and find basically like what's the average size of all of these squares that we can draw. And you might say, why do we do the squares and not just the lines? Because it's mathematically easier. How would we work out these lines? Well, firstly, if we didn't include the negatives, we'd get exactly 0, because that's how the mean is defined. The mean is there to be the average number. So by definition, we should have an equal amount of these lines, like the length of these lines, if you add them all up, would be the same on the right to the same on the left. So what we needed to do there was maybe ignore the negative. So just take the actual magnitude of these lines and add them all up and see what the average of those are. But that is more computationally difficult to do than just squaring. Because how on a computer do they take away, or like not take away, but remove the negative sign? I take a modulus, they square and then square root. So the variance is just a way that instead of having to square and square root every value, we just square them and then square root at the end. It's just a measurement. There's many other ways we could record this thing, but this is just a commonly used way because it is very mathematically simple. So that formula then, we want to find for every point, how far away is it from the mean, but do the square of that, and then take the average of those things. This is the definition, and will not be something that you generally use too often. How you're going to normally use it is if we expand these brackets out. I won't do the sort of proof of expanding the brackets today, not what you need to know for the exam, do you know what I mean? So doing that, what we're going to end up seeing is that it's the sum of the squares over n, take away the square of the mean. So it's the mean of the squares, take away the square of the mean. Sometimes you will see this written as x squared bar minus, I can get some more space, minus x bar squared. So do you square and then average, or do you average then squared? That's it basically. If you're wondering about this proof, expand the brackets out. Remember, this is actually just a constant, and everything will come out the front, and these bits should start appearing. Lovely. So that's good. Let's have a look at then what happens when we do these bits. Well, we're measuring spread. We're measuring how thick our distribution is. So if I just added something to it, like if we were measuring people's heights and we just gave them all massive shoes, do you know what I mean, like 2-foot tall shoes? The average height is just 2 foot taller, isn't it? But has the spread of it changed? No. How tall I am compared to how tall you are, that difference is still the same, just because we're both wearing funny shoes. So it doesn't change the spread. Whereas if we think about timesing it by a out the front, that is literally going to spread it out. If this was 2 and this was 8 and we double it all, this is now 16 and this is 4. The gap size was 6. The gap size is now 12. It has doubled as well. It follows the same growth rate, the same scale factor as the data did itself. So what we're going to see, if we think about applying this linear operation to the set of data that we have, what we're going to see is it's exactly the same as if we just times the variance of that data set by the kind of the scale factor we had just for the x. So the b goes away, but the a is included. Lovely jubbly. We can, sorry, that should have a square at the front. That should have a square. Because we squared the distances. We actually stretched everything out by that, but then I think we measured the square of that. So it should be scaled up by the square of that. We get the kind of following from that then, is that if we did this just to the standard deviation, we're going to get just a times that standard deviation of the actual original data set. So for means, if you multiply it by something, you multiply the mean. If you add something to it, you add that to the mean as well. For the variance, if you multiply by something, you multiply by that thing twice, like squaring it. If you add something to this and then do the variance, doesn't change it at all. So it's just sliding this distribution from here to over there. The shape of it is still the same. Lovely jubbly. So that's the kind of kind of what you'd call them. You know, mean and standard deviation is in one group, and then we're going to have the quartiles in the other one. So looking at that, what do we have? Yeah, the quartiles. Not too bad of a thing to think about. So quartiles. Again, you'd have done this, hopefully, in GCSE. Fingers crossed. How much you do it compared to here? You'll cover most of it. Do you know what I mean? Most of it you'll understand what's going on. Because you've done box plots, which we will talk about again in the graphs, but most of it will be covered here. So the quartiles themselves, here we're looking at the pure distribution. We're measuring this in whatever units we're measuring it in. This has units of the units we're talking about. Could be meters, could be people, could be whatever. The quartiles are the same idea, but we're talking about now kind of percentages. It's about the distribution of it in terms of percent. Every quarter of the population, we're going to split into it like 4 groups, that's each 1/4 each. So the actual things you need to know about, generally we're going to write them as Q0, Q1, Q2, Q3, and Q4. Some of these pretty straightforward. Q0, the min. Q4, max. Q1 is the lower bound. Q3, upper bound. No, bound, quartile, sorry. Quartile, not bound. Lower quartile and upper quartile. And then the Q2 is the median. So the middle value. It's literally the person that is slap bang in the middle. So we've got half as many people less than them, half as many people more than them. They are the bog standard average Billy. Do you know what I mean? Average Billy. No more Billy doing weird things with, what was he doing last week? Last week he was pulling carts when he at weird angles. This week he's slap bang average. He's doing nothing strange. So he is right in the middle. These are useful then for box plots because we can draw them and they show a very quick distribution of the data. You're always going to see Q0 down there, Q1, Q2, Q3, and Q4. And here what we can see is that we have a roughly even spread on all of ours. Maybe this group's a little bit smaller, but there's a big trailing end. Big trailing end down here on the lower one. How we can then turn that into one of these graphs, well, from one of these graphs into like one of these graphs, isn't too bad. We know that the peak should happen here because it's the median. No, that's the mode. Yeah, the peak shouldn't happen there, but we should have this as the exact middle of the graph. But this one with a long tail is going to go that way. So it's going to have something like this going on, where this was a much shorter tail and this was a much longer tail. Oh, I didn't write down. Which way is that? Is that going to be positive skew or negative skew? Positive skew. Which way is that going to be? This is negative skew. This is negative skew. So it's kind of the wrong way around, annoyingly. Negative skew is to the right. And if we look at another thing the other way around, we're going to have positive skew doing the same thing, but that way. So this is going to be positive. And here you'd see a very similar box plot, but almost a mirror image. We're going to have some big amount of them there. Short tail on the right. Sorry, short tail on the left, long tail on the right. Maybe that's a way of thinking about it. This one points off the positive. This one points off to the negative. So that looks good. The other thing to do then on these is finding, well, we should mention interquartile range, I suppose, actually. Like, you know what that is, yeah? This bit along here would be called the interquartile range. It's the range between the quartiles. Yeah. Yeah. You know what range is, yeah? Min and max, how far apart are they? Interquartile range, same thing. But instead of being the very top, very bottom, we're looking just at the kind of middle half. Because this is exactly 50% of people. 25 in there, 25 in that one. So together, 50. So we're looking at the range of the middle half of people. Benefits and drawbacks to each then. This includes everyone. So if you've got one weirdo that is like 12'4" and everyone else in your school is 4 foot, that one weirdo is going to drag everyone up. And you might end up in a situation where you're going to have the average height is 5 foot. You've got one person taller than 5 foot. Everyone else is beneath it. Because he's such a giant, it's been just completely swayed by that one person. So that's why these are going to be useful, because they don't count the outliers. The outliers, you can either have them in this group or you might just see them over here doing something like that. But generally, we're going to talk about these middle sections where the top 25, bottom 25 were ignored. So if they even say they had much more influence than the other ones, they don't get counted in these ones. But they do up in these ones. That's why certain data, so for example, the incomes, average incomes in the UK, is normally done median. Because if you do median, you get, I can't remember exactly what it is. It used to be like 30, like low 30, something like that. But if you did the mean, it was about 15 grand more than that. So what they're saying is that if you were to order everyone up, the middle person earns, I think it was 35-ish, we'll say 35, roughly grand a year. But because some people earn so much money, the actual average is closer to 50, 45, 50 if you added up all the money and divided by the people. Because what we have is a distribution that is positively skewed, i.e. loads of people are poor and broke, and you've got a few rich cunts taking all the money away. So it ends up being that the mean gets dragged to the right of the median. So if we look at that, what we're going to have is the mean is over there, and the median is going to be there. The peak is always the mode. We don't really care about the mode too much here. And for the negative, then obviously the other way around. We're going to see that our mean is being dragged to the left by all of these people, but our median is on the right of them. So that's generally the difference between negative and the positive. Which ordering do we have here? Which one is higher? Which one is lower? But I think it's easier to see from the shapes. Just trying to remember which one, which way around each one is. Last bit in here then you need to remember is about the linear interpolation. So if we know we want to find the median basically, and we have the groups, we want to find where inside that group the median is. So let's make something up, probably easier a little bit here with examples. We're going to have some group that's just going from 20 to 30. So it's like, say, how long it took to walk somewhere or do something like that, yeah? So this is going to be our class. And we'll have a frequency of, let's say, 15 people. From that, then, we can be told the kind of frequency beforehand. So let's have some cumulative frequency. And let's say as we came into that group, the frequency beforehand was already 42 people. We've got some other numbers there. So now we have 57 altogether. What our goal to do basically is figure out in this group, where are we? We might know that the median person, so the Q2 index, was number 50. So our job then, if we were to order these people up, we have that the 43rd person is the first in the group, and the 57th person is the last in the group. Got that slightly wrong. We don't need the 43rd. It's a bit weird to think about. So it depends exactly where you put the people. So this will be 42. This will be 57. We know the median was number 50, yeah? So this bottom row is literally the positions of the people. These are the indices. The top row then is going to be the actual values they represent. So we started at 20 and went to 30. And the middle will be the number we're looking for. So we're using this because we want this to be proportional. The top row needs to be proportional to the bottom. How far through the group we are in the position, in terms of the indices, should be how far through the group we are in terms of the actual units we're talking about. So we're going to want to take this bit and color code everything. We're going to have this red line and this green line. And then we're going to have a pink line up here and a yellow line as well. And what we want to do is find out how far through the group we are. So first of all, Q2 is definitely going to be, Q2 is going to be at least the lower bound. So it's at least 20 here. Because we want to think, okay, we've got to the start of the group, and then how much further through the group. So actually, let's write down a kind of a general form. It's going to be the lower bound of the group plus the percentage through the group times by the class width. That's what we want to find. So lower bound plus what percentage are we going to get? Well, we can get that from the bottom. We've got the red bit, and we're going to divide that by the red bit and the green bit when we add those up, because we want to find effectively how much of the group have we done. We've got 8 out of the 15 altogether. So plus 8 out of 15, because we were the 8th person in the group of 15. Yeah, nice and straightforward. This bit then, class width. 10, yeah? Times it by 10. What that's doing then, this little fraction, or this little section of it, percentage for the group, class width. Finding out, instead of being percentage, turning it into the units we're talking about. Add those up, what we're going to get, some number that represents the actual value of the median in terms of the units that we are measuring it in. So if we do that quickly, what's 80 on 15? We get a number of 5.3-ish. So we end up in a situation here where it's going to be 25.3. And that kind of makes sense. We were 8 out of 15th, kind of halfway, and we're kind of halfway, just a bit over. Lovely. Spot on. Let's fit it in with our colors quick. We're going to then add that onto that fraction of 8 was the red on the top. Sorry, put it on the fraction, don't I? Yeah, add the 20 onto the fraction there, times by the class width. So times in this by the pink plus the yellow. And that will always give you the quartile. This also does work for every other quartile. Doesn't have to be just the median. Nothing here about the 2 was important, was it? As long as they match, we're all good. So if you know the index, the position of the thing you're looking for, you are hunky-dory. You're A-OK. You're ready to rock and roll. Just fill this thing in and you should be good. I think it's easier to maybe think about doing this and remember the ideas of like this bit. I want to work out what percentage it is and then just times it by that width. So maybe think about the either the formula or this diagram. Either we want to do it, should all be good. Lovely. Right, graphs then. So we just did interquartile range and stuff. So box plots are one of the graphs. We covered that a little bit, but I'll just write them down again here. So yeah, all the quartiles, that's why we do them. Q0, Q1, Q2, Q3, and Q4. So every single one of these little sections is 25% of people. That's why we do it. So we can see roughly a distribution of the actual groupings of the people, the population, not just the kind of extreme values. It focuses more on the middle group where the vast majority of people are. The extreme values, how do we decide whether to count them or not? When we have outliers, what classifies something as being such a weirdo, we don't want to consider it. Because that's what outliers are. It's having some stranger that's watching you from the corner and we're like, nah, we don't really want you as part of our data set. We're going to put you over here. Do you know what I mean? You get a special mark. We're like, you were here. You were here. Yeah, you were here. I'll give you that. You were there. But we were here. Do you know what I mean? You were over there. So that's what we're doing. We're trying to determine how much of a weirdo is this piece of data. Are we letting it in the group? Or are we just thinking, nah, nah, you could not be part of our diagram. We're just going to mark down that you were so strange that we don't really want to consider you with everything else. How we do that, again, subjective. A lot of stats is going to be subjective. Someone's just decided, oh, this makes sense, let's do this. So generally for outliers, what we're going to see is if we are more than the upper quartile plus 1.5 times the interquartile range. So if we're bigger than that, or if we're going the other way, less than the lower quartile, take away 1.5 times the interquartile range. So effectively, we're getting this line, getting half of it, sticking those tail to tail, and then we're going to go and make sure, put that back, we have these sorts of ranges either side, and if you're in the blue bit, you're A-OK. If you're not, well, and this bit, that bit's fine too. If you're outside, so if you're in this section, nuh-uh, you're not in part of our group. We're going to exclude you from the data because you're such a weirdo. So they're outliers. They might tell you in the question, we're using a different way to define outliers. Fine. Just plug in the numbers you have, see if it fits. They'll give you some information about these bits. Or it might be done with mean and standard deviation. And they might say anything more than like 2 or 3 standard deviations from the mean is too much. So it could be, yeah, similar idea, but if we're too small, we could be the mean minus, that's not a minus, is it? Minus 3 standard deviations, or it could be this side, mean plus 3 standard deviations. Yeah, plus this way. So again, they could change this number. They could change this number. In the question, they will tell you. If they don't tell you, you can assume one of these. I don't think this is in your book, but this is generally like what's done. I don't know if that's actually in the Edexcel textbook, but they will tell you if it's something different than this one. So they're the outliers. They're not too bad. And they work generally, yeah, with the graphs. And we would just have a situation where we have some outliers up here. And you mark them off If you want to do a star, do a star. If you want to do a cross, do a cross. If you want to circle them, circle them. As long as it's very clear that they are outliers. If you're not too sure, just do that, do you know what I mean? Make it clear. They are outliers. Lovely. Other types of graphs then, again, you'd have seen these before. We're going to have cumulative frequency graphs. So we've got some cum freaks. Everyone loves a good cum freak. So what do we need for cumulative frequency graphs? We're going to have on the x-axis, generally, it's going to be the units you're talking about. So it might be meters or seconds or something like that. And on this side, you're going to have the actual count. So this is going to be the frequency, obviously cumulative frequency, but it's basically the number so far. So it's the count of people. And you'll see something like this. Not like that. It can never fall back over again, do you know what I mean? But we could have very different shapes. We could have something that goes like very quick and then is flat, or the other way around, where we're going to go through and have something that takes a while to get off and then goes. Whatever shape appears, we can do very similar things, where we're going to take the count on the y-axis and change it to be really percentage. So having like this is going to be 100%. We can have then the middle people 50%. Have the bottom ones. I'll make this match up. Of 0%, and then the quarters as well. Can you see where this is going? And then from there, every single one, my mouth gave up there. Lovely. All of these marks then, alongside this one down here for Q0, are going to become a way that we can turn this cum freak into a box plot. Bop, 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 bop. Big tick, 4 marks or something silly for doing that, yeah? Just draw lines, draw lines, draw lines, and then just keep drawing lines. And they generally, when they give you the graph, you will have another graph underneath. It's very small, but it has the exact same x-axis. Exactly the same thing's been given to you, just in a different graph, in a different thing down here. But it is identical to the version given to you above. Lovely. Hopefully not too bad. Nice and straightforward. They might make you work out like the cumulative frequency and then draw it afterwards. Straightforward, yeah. You just, if you have 70 and then 30, the next row down, like that's 100. 70, if this is 40, it's now 140. You're just adding as you go, yeah. You're accumulating things. You're gathering them up. Last thing on here then, histograms. Again, you would have done these at GCSE. So it's all repetition from what you've seen there. So histograms. Main thing to remember is going to be that we have our x-axis, again our units, and then the y-axis is not the frequency, but it's the frequency density. So it's a dense freak. We have to think about every single bit that we get. We have basically the area is the frequency. So if we were to take just like one actual box by itself, what we're going to have is that every single box that we get is going to be the units. This would be the people, and then this is going to be people per unit. And this is really useful, people per unit. And the whole point of why we do box plots is because it's effectively taking a big box, a big group of things that we got, and splitting it into bars, where every bar is just like one person. This is like 1, 2, 3, 4, 5, 6. And then we're seeing actually what was the frequency of that, or maybe not person, but group. Do you know what I mean? What was the frequency of each one individually? But because we didn't do them individually, we can't say. We've only done them as a group. So we're just going to say it's the same everywhere. And that's what histograms do. So how are we going to work things out? Look at what they've given you. Look at all the boxes and go and think, basically make this equation. The units times the people per units is going to give you the people. The units times the density gives you the frequency. So we literally have the main equation. Frequency is equal to frequency density. Maybe the other way around, actually, probably better way to think about it. Frequency density is the frequency per the units. Like per unit. Do single unit there. Because that's what always density means. It's how much stuff and how much space. You have kind of population density, how many people and how many square kilometers. You can have just mass density, how much mass and how much volume. So anything, it's almost how much stuff in how much space. They might make you do some weird things where you want to work out like quartiles. In that case, you can go through and work out like how big is one of these squares? Is that 2 people? And then just go through and keep going. Like, oh, this group takes me to 10. This group gets me to 25. I need to be number 30, so I need to get 5 people out of that group. Either count the squares or think, okay, I need to get 5 people out of that group. It's 30 altogether, so I need to be 1/6 of the way through. Work out what percentage of that group you need to steal. Draw a line that percentage of the way through it horizontally. As in you traveling through horizontally, but you draw the line vertically. And then whatever number you get out there will be the value you're looking for. I think that's it. I think that's it on the graphs, but it does lead us on very nicely to like scatter graphs and correlation. So scatter graphs, I could kind of put them here. I mean, they could have gone in this one, but correlation is kind of how we're only ever going to talk about them and use them. So we'll talk about it from that bit. But what this does do, this brings an end to our kind of foundation section. So those bits, hopefully, you've seen most of those before, or at least come across them at GCSE, or like the sampling stuff, it's just pretty straightforward, yeah. It's just a case of like memorize these facts, learn how to do these processes, and then when they ask you, it's just like 1 or 2 markers. How do you do what's the difference between a sample and a survey? Survey, you ask a sample and a census. Census, you ask everyone. Survey, you don't, or sample, you don't. Nice and straightforward. So correlation, let's go. Correlation, what is it? Well, let's look at the word. Relation, co. 2 things, multiple things together, yeah, for co. You've united, you're cooperated, you're doing, there's 2 of you, you're together, you're combined. Relation, how are you connected? What is your connection? So today, correlation is looking at the relationship between 2 things. How are they affected? What it is doing is talking about the data and how they're related. What it's not doing is talk about why. We don't care about why in maths. We just care about how and what, not the why behind it. So correlations we're going to see then, we'll use the scatter diagrams. We're going to have some value on this side, say this is going to be the x's, some values on this side, say the y's, and we will get loads of data points. You might have how fat people are and how tall they are, and you get this distribution that kind of follows a nice line, and we can draw a line through it. Because this is going up, this has a positive gradient. It is a positive correlation. So whether it's positive or negative is simply whether the gradient of this is positive or negative. Do they go up together? Do both of them get bigger together? Or do we see the opposite? Do we see it where we have something going down? We have some values for x, some values for y, and we're going to see them going in a downward gradient. The actual gradient itself doesn't change the strength of the correlation. So having this being steeper and say one being shallower, that doesn't change the strength of the correlation. It's simply whether they're going up or going down. What affects the strength of the correlation is going to be how tight these are to the actual line themselves. So the way we do that is going to be to look at, again, we'll get some random data, do a few less, it's easier to talk about. But say we had all of these. You can see we're kind of going up, yeah? The way that we were taught to imagine it is that we have all of these little lines. And we're effectively going to imagine that these are rubber bands, yeah? Little bungee cords. And together, what they're going to do is try and get into the simplest solution they can get by being as short as possible. They're all pulling on it, and we're going to end up with these being the least amount of length in total. And that means that they are therefore like the least distance away from this line. We're looking for like the lowest average distance away from that line. That is the correlation. If these are on top of each other, it's perfect correlation. If these lines get massive and they're nowhere near to do with this line, it's weak correlation. So the distance, like the total length of those green lines, measures how weak a correlation is. The longer those lines, the weaker it is. So if we have longer green lines, that implies a weaker correlation. We want to have our things as tight as possible to that line, not being very far away from it. In reality, it works out much like the variance thing, where we actually are looking at all the squares. Do you know what I mean? We're really looking at all of these squares and trying to make the squares as small as possible because it's just mathematically easier. But exactly, completely fine to think about it in terms of these linear versions. Same process. You don't actually ever need to do the process of working it out. You just need to understand that this is what the process is. This is how it goes on. Good, lovely. The strength of these then is going to be all about, yeah, how close to the lines they are. So we can get some versions. Let's get 4 little axes and we'll look at all the 4 different types. So we can have a strong positive, we can have a strong negative, we can have a weak positive, where we've got more of a spread around that central line, if we draw the lines of best fit through it, and also a weak negative. So what have we got? This side on the top is strong and weak, and then we're going to have positive and negative. You can obviously get no correlation as well, just when like it's just doing random things. I mean, there's no fit to it. You've got something and it's just kind of everywhere. There's no real pattern to it at all. We'll put that down here maybe. So we can have this sort of idea where like you can't really draw anything. Like which way is the line of best fit there? There isn't one, is there really? So this would be just no correlation. Any line of best fit you draw isn't really any better than any other one. Do you know what I mean? They're all kind of just doing nothing. So we just say there's no point. There's nothing to do with each other there at all. That's good. The thing that measures it then is going to be the PMCC. So that is the product moment correlation coefficient. So very fancy words. It's just a measure of correlation. Product moment is something about like moment is to do with averages. Product is obviously multiplication. Correlation, coefficient, just a measurement, like coefficient of friction. Do you mean how strong is it? 0 to 1. Similar sort of way, we're going between a max of 1 and a min of -1. So the idea positive, negative, we're saying that 1 is the maximum strength of correlation you can get. Like 1 is the biggest magnitude you can get. That all looks good to me. Anything else on there we need to talk about? Yeah, exponential stuff. So these obviously are always talking about straight lines, yeah? Straight line relationships. There's no point trying to get a line of best fit when you have a curved relationship, like a square or something like that, or an exponential relationship. So always what we want to do in those cases is to transform them from exponential into linear things. So if we have your exponential models or relationships, we're just going to use logs and we're going to turn it from something where it is like y equals ax to the n. Taking logs to both sides, what do we get? Let's do ln. We'll have the log of y is equal to the n times the log of x plus the log of a. So falling it into y equals mx plus c. If you do physics, you will recognize this. Like you're doing this all the time whenever you're kind of plotting the graphs at the end. Do you mean? It's that same process. So this is true whether or not you have like whichever you want to do it, it should be fine. Whether you have like an exponential thing you're doing or where it's just like square and you're still looking at the x's. Same idea. Then we're just going to plot this one down and do the same stuff as we were doing before. Same as above, but now instead of having x and y, we have log of x and log of y. But all the same facts are true as above. We can talk about the correlation of log x and log y. Same process, you've just done a log bit beforehand. In anything you get, basically, you want to turn it into straight lines and then deal with it. You don't learn how to deal with like bimodal distributions, like one where you have like 2 peaks and things like that. Do you mean? You don't know how to deal with that. You only learn how to deal with stuff where it's just like one peak, one thing is happening, one explanation causing something else to happen. That's all good. Correlation again will come up in hypothesis tests. So it's going to be actually most of the time you're using it is really in a hypothesis test. Right, yeah. Let's keep going. Next thing is going to be, we skipped one, is probability. This is effectively what I'm studying at university. it's going to be this, like it's this and tree diagrams, but they're not trees anymore. And you're seeing like as you move around this network of things, what's the probability of you being in a certain place, or it's like a distribution of people being in these different positions in this network. You might think about like the tube map. If we have all of the kind of stations on the tube map, you can imagine having like, oh, we have 3 people there, 2 people there, 5 over there, 4 over there, 5 in that one. We let all the trains go, and then we get new sets. We have now 4 over there, 3 over there, 2 over there, and 3 over there. And it's like, where did all the blue people move, and how have they become green people? And think about those probabilities, and what's the chance of you ending up in certain places, getting bottlenecks, that sort of stuff. So this is like, yeah, very much the prerequisites to what I am studying when I go do my masters. So it's pretty simple. There's not a lot to it with probability. There's some formulas to know, some definitions to know. Apart from that, not a huge amount. If you know the formulas, know the definitions, know how to translate the English into the maths, you will be able to do the maths. This is the whole thing in the applied section. The maths of it isn't anything more difficult than you were doing in like year 9, year 10. You can do it all. It's just a case of, can you understand this English and translate it to maths? They do a terrible job in the UK at teaching mathematics as a language, just teaching mathematics, but teaching it as a language. The entire thing has structure and grammar and rules that you must follow. And how does this sentence in English translate, literally translate like a language, into mathematical notation, which then we can work with? So that's going to be a lot of it. Let's start off then by muting my phone, because I don't care about the IP of SpaceX at all. And then let's think of our definitions. So definitions, what do we have? The first thing is going to be like just an event. What is an event? That's something we do. So an event is the actual like rolling the dice. So here we are rolling the dice. That is the event, the act of rolling it, the doing of the roll. The outcomes then are evidently the things that can happen from that event. So this is like getting the number, getting the result. I.e., all the different ones we can have. 1, 2, 3, 4, 5, 6. It's every single thing that could happen. Yeah, maybe let's change it like it's all the possibilities. So it's all possibilities. When I roll a dice, what can happen? This is all that can happen. I can't get a 4.2. I can't get a turtle. I can't get a 7. I can't get a cat. These things are not allowed. All that I'm allowed to get out of it, all of the possible outcomes, what can come out of this event, is numbers 1 to 6. From that then, we'll talk about the kind of sample space is kind of the same idea. Do you know what I mean? This is the word really for sample space. And then you talk about an individual outcome. The collective of outcomes is generally called the sample space. And then each one individually is one single outcome. That's good. So some bits inside probability then, once we go looking past this, are going to be Venn diagrams. Again, hopefully you have done those. There's a few things to think about firstly with Venn diagrams. There's no need to really do circles. One thing I'll do today is like my Venn diagrams are often not going to be circles today. Most of them will still, but we're actually just going to have like squares to represent the different groups that we have, the different sets that we're containing in these Venn diagrams. So no reason why they have to be circles. We have obviously the universal set. What does that mean? It is the universe. It's everything we care about. Everything we care about. Anything outside our universe, we don't care. We don't give 2 shits what's over here, what's over here, or over here. If I'm asking questions about the students in your school, I do not wonder or mind or care what Doris at the bus stop thinks, or Billy at the school down the road thinks, or your mum, or me. We are not members of your school. So we are not part of the universe that we are considering right now. And then each one inside there is going to be a set. The word set here, it does have a different definition than just like group or collection. It's got some special rules that can happen with it. Those rules do not affect you in any way, shape, or form at A level. I'm 99.9% sure. Like it does not matter if you said set or class or group or collection. Do you know what I mean? All of them would be fine here, but set seems to be the one that they've used. But I don't think you actually need the rules the extra conditions like a set is. Why is that a different type of like class than something else? I don't think you need those rules here. I've never come across a situation where that's mattered at all. So just a group, a set, Jimmy, collection, group, anything like that. Happy days, all good to go. From that then, let's do some colouring. What bits do we have? Well, if we label this A, label this B, we've got this blue section. That blue section is going to be the intersection. Let's do that a bit nicer with that one. So intersection. You need to be in both. Both. Let's do that in capitals, actually. Both A and B. Not just one of them. This blue section, where am I right now? Am I in the B circle? Yes, I am. Am I? Oh, I say circle. Am I in the B set? Am I in the A circle? The A, the A rectangle, the A set. Yes, I am. So I'm in both of them. If I do the other idea and look at kind of just being either set, that's going to be the union. I can be here, here, or here. So the green one is the union, is either A or B. Another way to think about it, which is quite nice, is how many ticks do you get? If we go and like kind of ask the question, am I in A? Yes. Yes. No. Am I in B? No. Yes. Yes. One tick is union, like at least one tick is union, but you need 2 ticks for the intersection. Because asking the question and I need to satisfy both conditions. So for the union, I just need to satisfy one of those conditions. That's good then. That's the Venn diagrams. And again, hopefully you've seen them a lot. Do you know what I mean? In your life. You've just dealt with them day to day, all the time. Shouldn't be something that's too scary. Let's move this over a little bit. Some other things to think about then with these are going to be a few more, like they are kind of definitions, but they're a little bit more involved, and we're going to have some mathematical thing that comes with it. So what I was saying about having like the English and translating into the maths, this is what we need to do for these little words. So let's list them. What have we got? We have, let's make some space first for them. We're going to have mutually exclusive. We're also going to have independent. Independent. We're going to have exhaustive. Is there another one? We then have a conditional, do you mean? But we'll speak of that in a second. So mutually exclusive. Well, what does it mean to exclude someone? You know what it means to be excluded. What it means to exclude someone. We don't want them as part of our group. They are not part of our group. Like the outliers we had on the page before, or the page before that one. The weirdos, they've been excluded from our group here. We have mutually exclusive sets of the ones that we've considered and the outliers. There is no overlap. They have been excluded from the set. And the mutually means that they've both done it. So we have set A and we have set B. If you're in set A, you cannot be in set B. If you're in set B, you cannot be in set A. If you're friends with me, you can't be friends with her. If you're friends with her, you can't be friends with me. It's that sort of scenario where our Venn diagram, what happens? Well, we have 2 sets, but those 2 sets do not cross over. So the maths that we want to get from this, I'm just going to shrink that down a little bit. The maths we get from this is that the union is empty. No, the intersection, sorry, intersection. Intersection is empty. You might see this written in terms of sets like that. Mostly, you're not going to deal with that. So I'm going to keep it in the way that you'll deal with it. The probability of being in the intersection is 0. We cannot be in both. Cannot be, it's not B. Cannot be both. You must pick which group would you like to be in. Another one then, looking at that, is going to be the exhaustive one. This is kind of the opposite. So you see here, like, we couldn't be in both. Here, we must be in 1. Must be in 1. We're not allowed to be excluded. We must be part of the group. You cannot be a loner, cannot be a weirdo. You must be included. So for the exhaustive set, what we have, notice here we didn't care about the universe. Our universe could have been massive, could have been tiny. But what we did have was there was places outside of these ones. We can get it where mutually exclusive does take everything up, and we'll look at that in a second. But for the exhaustive, we cannot be outside the group. If we go and draw the universal set, yeah, that's not a very good one. That's an even worse, but it'll do. The two sets that we have must occupy the entire universe. There is no space outside of the green or the blue. There shouldn't be this, like, you shouldn't be able to be there, do you mean? There is no space outside the green or the blue. You must be in either one of those. So what does it tell us mathematically? If we consider the probability of the union, it's 1. We have to be in one of them. No choice. Absolutely no choice. You are either in school or out of school. You are either a potato or not a potato. There is no third option. So being a potato and not being a potato are mutually exclusive groups. They are the kind of antithesis of each other. We could have cases where they overlap. So what we've actually drawn here is both mutually exclusive and it's exhaustive. Because not only do we take up the entire empty set, entire universal set, but they do not cross over. We cannot be in both the blue one and the green one. We can get the opposite then, if I can slide this out of the way. Not the opposite, but like the other case, where if we have our universal set, and we have our blue set, and we have our green set, they do have some overlap. There is some section where you can be in both. You can see why the squares are quite useful here, because now there's no edge. I mean, trying to get the circles to fit, they're not going to fit really. The edges, the squares don't still do too well. But here we do have some overlap. So this is going to be mutually exclusive. But this is not exhaustive. No, sorry, not, what's the word? No, other way around. It's not mutually exclusive, but it is exhaustive. Because we cannot be outside the groups, exhaustive, but we must be in one of them. Lovely. Next bit then, for probability. You can have tree diagrams. We can talk about those a little bit, I suppose. So let's do that. But actually, no, let's continue. Let's do the independence I was on about. No. We'll do the trees first. I think that actually makes more sense with the order. We might need 2 pages though, so let's get a new page probability. So here we have prob part 2. So let's think about tree diagrams. Everyone's seen a tree diagram, Yep. We're going to start from down here and then have all of our branches go out. Branches go out there, branches go out there. What we have, all of these, do a different color for them actually. These are all different states. They are going to be the states of the thing you're talking about. So for example, if you're picking beads out of a bag and you have 10 red and you have 10 blue when you start, here will be 10 and 10, won't it? That's the starting state. Here would be 9 and 10, and this side will be 10 and 9, because they're the 2 possibilities that can happen when you take one out. Let's actually fill these in a little bit better. So we can have 10 to start with for red, and we'll say that going up is picking those out, and going down is leaving them in. So this side will be 10, that will be 10, here will be 9, here will be 9. The blues then, we could have 10 there. We didn't pick one this way, so it's still 10, but we did when we went down, so there's 9. And this one would have also a 9 there. This would be an 8, and this would be a 9. And you can see now we actually get a collection. So this would not be a tree. This is what you don't learn about. This is the bit I learn about. These can then join back up again and not be trees. You can end up in the same state in kind of 2 different ways. I think they call it, is it transposition? I think that's what they call it. Yeah, I think it's a transposition when you go like that. It might be something else. I'm thinking of the word in chess. I can't think when you do that. Is it transposition? Maybe, but you don't need to know about that. What we can think about in this case, though, what bits do we have? Well, when we look at these trees, let's think about actually doing, this is going to be going to red, yeah? Going up, and then blue going down, so it's going to be red. This is going to be red, red. This is going to be red, blue. This is then blue, red. This is blue, and this is blue, blue. So the different states we can get to, just marking the states there again. But as we move then from the initial state up this way, it's the probability that we picked out a red one. And this way, probably that we picked out a blue one. And then going down, we want to pick a blue one again. But we've already picked one. So the probability that we pick one again has been affected by the fact that we already have picked one. There's now only 9 blues. So it's only like 9 out of 19, not 10 out of 20. So what we have with tree diagrams is conditional probability. Because the branches are different, aren't they? If I go down to this one, the branches I get from there are different than if I'm at this state. It depends on what state I'm in. There's conditions on the probability. It depends on what has already happened. So this branch will have the probability that we pick a blue one, given that we've already picked a blue one. This version will be very similar. We now think about wanting to pick a red one, given that we just picked a blue one. So the conditions are based on what's already happened. That's all we're saying with the conditional probability. We are interested in what happens if something else has already happened. How does that affect us afterwards? How we're going to do that then, either with trees like this, or we have the formula. So we say the probability of A given B. What's the chance of A happening? So if B happens, what is the probability of A? That is what that thing is saying. If B happens, what's the chance of A? You've seen this notation in set notation. What type of number is X? What are the conditions on X? What rules do I need to have passed to then have a look at these things? What rules do I have before I look at this thing? The formula for it then is a little bit easier to kind of build up when we look at Venn diagrams. So let's just have 1, 2. Generally, when you have the universal set, you're really thinking about like, okay, well, we've got, let me just draw that. We've got this universe, yeah? It's everything we care about. The probability of being in A is the chance that, like, of all the things that we have, whether they're in A or not, we're going to work out basically, let's do it over here. The probability of A is going to be equal to the number of things in A divided by the number of things in the universal set. That's how we work out probability. If I have 1,000 things and 50 of them are in group number A, then I have a 5% chance of picking something from group A, because 5 out of 100 of them are that thing. That's what we mean by percent. Per cent. Cent, century. Cent like 100. It's per 100. Look at the symbol that we have for it. The old symbol before that, per 100. It literally means if we had 100 of them, how many of them are what we want. So it's the same thing for probabilities. With a conditional then, we already know B has happened. So we're changing our universe to be actually just B. We're looking in, so we just have the B universe. How much of it is A? Well, that bit's A, isn't it? This stuff doesn't exist anymore. I don't care about anything around here. This is not part of my universe. I only care about this B circle. Let's give it a color. We only care about this green circle, and then we only care about the blue bits inside that. So what is the formula for conditional? How much is the blue bit? The intersection. over that green bit, chance of B. Everything that can happen is all the things in B. How many tick our box of getting A as well? Just those blue bits. And this then is very much linked to independence. So if we have a little thing about independence, let's do it. Let's do that. Independence. What does that mean? They don't affect each other. You've been dealing with this before you dealt with anything else, really. This is like the first way you learn about it. If you flip a coin and get a heads, wonderful. Flip another coin, get another heads, wonderful. Coin A, well, flip 1 and flip 2 did not affect each other. They were independent. How do we write that mathematically? The probability that A happens is the same whether B happens or it doesn't. This one, we don't care, do you know what I mean? This is what we're saying, like, it's always the same. If B happens, it doesn't change the general probability of it. You can also write, this is technically equal to, like, the probability of A given not B. That's completely valid as well. And there's stuff you can do with that mathematically, but it ends up being very similar, so you may as well just not think about that one. But it is also true. So let's take the formula we just had for conditional. Well, it was the intersection over probability of B. And now let's times through by this one. So on the left-hand side, probability of A times B. So probability of A times probability of B will be the intersection in the middle. So if this is true, independence is true. So we have this condition, independent A and B are independent if and only if that formula is true. The probability of A times the probability of B is equal to the intersection. Quick note on that symbol in the middle. Again, if you knew the language of mathematics, you wouldn't even need to be stopping to learn. What does that symbol mean? Imagine you wanted to write a story in English and you didn't learn all the letters, or you didn't learn that full stops were a thing, or you need capital letters in places, and you haven't learned these rules when you were 6, and then you go to university to try and write stories and do things, but you can't spell. It's going to be a lot harder to learn how to write stories and how to write things and read things if you can't spell, and you don't actually know the symbols and the letters that are used in our language. This means if and only if. The way that we can actually think about it, either both of these are true or neither are true. So both true. I'm going to change this to red actually. Yeah, both true or neither true. Both true or neither. They have the same truth value. It's how you kind of think about the proof by contradiction. You went through and every line you were doing, they had the same truth value because it was always this step in between. And then you ended up in it, the thing at the end contradicted one at the start, like they both can't be true. But you know they all had the same truth value. So they both have the same truth value, but they both can't be true together. So they both must be false. That was proof by contradiction. Simple, simple, simple. Here, it's the same idea. If we have this, they're independent. If they're independent, this is true. So you use it in two ways. If they tell you independence, you know this is valid. Wonderful. One more equation to work with. If they want you to prove independence, you want to find this on one side, find this on the other side, show that they are equal to each other. And contrary on that, like if you want to disprove independence, show they're not equal to each other. There's not, I don't think, any like nice graphical way of looking at independence. There's not a way I can draw down like, oh, look at these bits, do you mean? Like I've done this diagram for it. It's lovely. Look at that. Doesn't really exist for independence, I don't think. Not anyone that I've seen anyway. If there is, wonderful. Whack it in the comments. We'll put a link, but I don't think there's one I can think of the top of my head anyway. Anything else here? I suppose we've got one, maybe more formula we can put in that we didn't really think about. And that's going to be the addition formula. Again, one you might have just seen from GCSE. It's basically saying if we add up the probability of A and the probability of B. Let's go and do that in a Venn diagram, yeah? We can have universal set, we can have A, we can have B. As I go and add them up, what am I going to do? Well, for A, I get that bit and this bit. For B, I get that bit and that bit. So when we do that, we've counted everything, yeah? We've counted the union of them, But we've also counted this bit again, because we counted it first with A and then with B. So it's the union, but with the extra middle counted twice. This is the formula that's always true. You can rearrange this whatever you need. If you need to have the union, rearrange for the union. If you need to have the intersection, rearrange for that. But this formula is always going to be true, and it's called the addition formula, because you add them up. We add them up and we get too much because we double count the middle. You can see cases then if we talk about mutually exclusive ones. Let's do it like this. Mutually exclusive. So they don't cross over, i.e. this bit is 0. What we get is that the union is just the sum of the two. This, again, you've dealt with at GCSE. The outcomes you get were mutually exclusive from the tree diagrams. You walk through here, you do all your flips. I'm going to ignore this part of it, but you do all your flips. There's no way I can get 8 reds and 10 yellow, 10 blues, while also getting these ones. I have to do one or the other one. So these all add up to the union of them, do you mean individually, and they don't really intersect each other at all. There's no intersection going on. Exhaustive ones, you can kind of think about the fact that we're going to have this will be 1 for exhaustive. That's the only thing that will change with it. We will put that down. So if they are exhaustive, we'll rearrange. We'll have that it's the probability of A plus B. Take the intersection, and that should be equal to 1, i.e. the union. If we had both of them, we'll actually put that up here. Did I write the formula for both of them up here? Wherever they both were. That's on this page, wasn't it? Mutually exclusive. So when they were both, this one was both, what we have is that probability of A, let's do blue again. So yeah, mutually exclusive and exhaustive, probability of A plus the probability of B is equal to 1. Because if we go and look at that formula, what did exhaustive tell us? We had to be everywhere. This is a big fat 1. And exclusive told us we had to have a big fat 0 there. So replace this whole right-hand side with just a 1. A plus B equals 1. And that, therefore, is what we write down for this one. Lovely. Is that everything? I think so. Probability looks good. What's next? Distributions. These are ways of talking about probabilities, but for many things at once, all the outcomes. On these ones, we're generally talking about like a few different types of outcomes. Do you know what I mean? A few different sets. Distributions, you're looking at like not sets of outcomes, but you've got every single possible outcome. You've got the entire kind of event space, outcome space, whatever they called it. What's the word? Yeah, sample space. So we're assigning a value to every single one. Let's think about distributions in general. What's a good example of something like that you've seen in just day-to-day life? Let's think about the weather. Up here, 24 degrees. Down here, 32. Over here, 30. We have given every point in space a value of temperature. You can get vector fields where we have something similar, but we have the wind. Windy up there, not so windy down there, not so windy on that side. We've given every position in the country a value of a vector for the wind. For distributions, we're doing the same thing. We're going to have all of our possible outcomes. Let's think about having like a roll of a dice. What outcomes can we get? 1, 2, 3, 4, and 5, because we ran out of page. So what are the outcomes? Are those ones? What probabilities do we have? That is what the distribution tells us. How do we work out what numbers these are? Or how does it tell us what numbers these are? One little side fact, hopefully you know, the sum of all probabilities is 1, yeah? Sum of all probabilities is 1. I don't think I mentioned that explicitly, but yeah, you know that, yeah? So we have that fact. Sometimes they'll use that for uniform. If we look at a uniform distribution, what does it mean in kind of mechanics? It's just equal distribution. So in this case, with it being a fifth, like there's 5 of them, we're going to get a fifth everywhere. The two that we learn about then that are non-uniform are the binomial and the normal. We'll start with binomial. Again, same word as like binomial expansion. We have two things, two options. What things do we need to know to be true to talk about a binomial distribution? We need a few things. We need there to be, we're basically doing an experiment, and that experiment is going to have two outcomes. You could think about flipping a coin, you get heads and tails. You could think about a lot more of the things than just two outcomes though, because we're always able to group them up into two groups. If I think about rolling a dice, I can get a 6 and not a 6. If I think about what day of the week it is, it's either Monday or not a Monday. If I think about what we are, we're either potatoes or we're not potatoes. Two possibilities, even though there may well be more than two outcomes, we're just going to artificially group them up into two outcomes, which then we can talk about. Further conditions then, we're going to do a fixed number of trials. How many things are we going to do? How many coins do we flip? How many times do we roll the dice? We want to know that before we start. Alongside that, fixed P. The chance doesn't change. It's not going to be affected by something else. We don't get better. We don't have outside influences on this. When we're rolling the dice, we're doing it in like the same space. We're not on one of them rolling it like down a hill or doing it somewhere really windy. Something like that. We want to have the same probability of success for each of our outcomes, no matter what's going on. They often are done as two, do you know what I mean? So that's three of them really. The fourth one then is they're independent. We don't want to improve. We don't want to get better by doing something over again. If you think about like, what's the chance of you running so fast? That is something that you can do binomial for a short space of time, but after a while, if you keep doing it, you will improve. And then the probability has not been changed, it's been changed. That's the point of it. They need to be independent to make the probability be fixed, really. And so they don't affect each other. Nothing that you do at the start affects the results at the end. It's almost like you're doing the same thing over and over, but they have no idea about it. Like when I roll a dice, it doesn't know about the 37th dice roll, does it? It doesn't know about the 400 before that. It only knows about itself. It's not affected by anything else inside the experiment. Notation for this then, we are going to have the name of our distribution, say we call it x, is distributed binomially, where we're going to repeat it so many times, a number of trials, and each trial has that probability. So this is the name, this is distributed binomially, where we have fixed trials, so fixed trials and probability. These two then, the n and the p, they are the parameters of our distribution. They're going to tell us exactly how the distribution looks, where it is, what it's doing, and the binomial tells us kind of how everything does it. We have general structure from here, and then this makes it a bit more specific about the case that we're talking about. So you could like flip it 10 times, have a chance of a half for each head, do you mean? But the binomial was telling us things about, oh, we had two outcomes. They're independent in each outcome we do. How are we going to use this? Well, we need to understand the difference between the PDF and the CDF. So PDF and CDF. What do they stand for? This is probability density function. And this is the cumulative. So think of it like the cum freaks earlier. It's the cumulative frequency. So the cumulative probability density functions, etc., etc. I will still write that density. What they mean in maths then, again, they all mean something in terms of maths. PDF, probability, the x is equal to a value. For the CDF, probably that we're less than and equal to. These are things that are true for all distributions, absolutely all of them. we would then look individually for the distributions. Do we have formulae for these? For the binomial, yes, we do. And actually, we do for all of them. But are we going to use it? Most likely, no, we're not going to use it. But in this case, we are going to use it. They might ask you specifically to use this formula to find one of the n's or the p's, to work backwards to get this back out. So what we have then is going to be, well, we want to get so many successes. What's the chance of success? P. How many of those do we want to get? X. If I flip a coin 10 times, I want 4 heads. This would be something to the power of 4, probably a half to the power of 4. So I want to get that thing to happen 4 times. If you, when you're at GCSE, wanted the probability of getting 2 head flips, you do a half times a half. If you wanted 4 of them, half times a half times a half times a half. You just do it to the power of how many you want. So we want that to happen. We also want it to not happen so many times. How many times? Well, if we want X successes, we have N total trials. The difference between those two numbers must be how many failures we want. So this is going to be number of successes. This is the number of failures. One thing to think about though, we can order these in different ways. If I think about flipping a coin twice and asking for 1 head, I can get heads then tails, or I can get tails then heads. So we want to consider the number of total ways, the different orderings that we can actually get to get this result still. That comes from the choose function. So we're going to have n choose x. So just to clarify, the probability of us getting a certain number of successes is going to be the probability of getting that success to the power of how many ones we want, times by the probability of not getting that thing, times by the power of how many times we want that to happen, times by the number of ways that we can get that thing. If you look at it without that part, it's basically just getting one of those orderings. What's the chance of one of the orderings? And this bit will multiply it to get out there to be several orderings. So this is unique for the binomial. It's worth noticing that this is just for binomial. Yeah, that is the binomial version. So what we could say, just to be a little bit of a fancy notation, just put it over here. The probability that x is given to x, or x is equal to x, given binomial, is that thing that we just found, n choose x, p to the x, 1 minus p to the n minus x. So you won't see that, but that is really what we could always say, given that this is true. Sometimes you just don't write down the given that things. I will rub that out because it's not something that needs to be in the notes going forward. Do you know what I mean? But it's a way that we could think about the notation we're using. How do we just use it day to day? What bits do we just assume and we don't bother? What bits do we just assume and we don't bother writing them down all the time? So let's get rid of that. But that looks good. Anything else about binomial? No, don't think so. Let's do normal then. So the normal, it is describing kind of the natural distribution of things that happen. If you have one of those Plinko machines, you know what I mean, where we have we'll have all the bits. We've got all these pegs everywhere. Do you know what I mean? We've got peg, 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 peg at the top, and I'm gonna have a little ball bearing that I drop down. Where's it going? Plop, 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 plop. Do you know what I mean? And it's gonna fall down, and then another one go through. Plop, 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 and then another one. Plop, 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 plop. And what we see after doing that, we get some distribution building up. What distribution do we build up? A normal one. It's just the natural one that happens. If you let things just randomly pick left or right, one or two options, what's going to go on? And we see it in a lot of other places. We just see it everywhere. That's why we study it so much. It's very much like we made this thing up. We worked out the distribution from this thing that's just completely randomly chosen, and we've just found that nature fits this thing. So why do you study these particular ones? Well, it's very easy to say, I do succeed or fail, isn't it? And these are just what happens in nature. There's other ones you do if you're doing further maths that are similar. You might think about the rate that things occur at. I do something per hour or per minute or per day, something like that. But we don't do that in single maths. We're just going to do the normal and the binomial. So normal then, we don't have the formulas. There are formula. We just don't do them at A level. They're a little bit too complicated in what goes on, and actually, I don't think we can actually solve it. I think there's something like we just know all the values, but like there's something about like we can't actually solve the integral that we that we need to do to get it out. So we don't do it A level. It's not something that needs to be dealt with. Same thing here. Like you're not going to be asked to do the sum of this over all the values of x. Do you mean? Not going to be asked to do the sum of it. Hence why I didn't write one down. The normal then, again, we don't get the formula. What do we want to do with it? Not a huge amount in terms of anything different than just using the calculators to get the values out. How do we write this down? We're going to have x is distributed normally with a mean and a standard deviation. And a variance. So we'll put it down. That is variance in there. And again, different notation. X, the name of the distribution, is distributed normally. No, it's distributed normally with a mean of mu and a variance of sigma squared. Conditions we need for this then are generally it's going to be like a symmetrical distribution, so it's like no skew. I will double check exactly what they want. I didn't write this down. Give me one sec. What are the assumptions of the normal distribution? It's going to be that we have like an actual mean and standard deviation. There's like some random process going on. So the assumptions are just it's normally distributed. Yeah, so what we have is that it's going to be a no skew, so asymmetrical. So symmetrical. And it should also have the kind of equal measures. So where I was talking about like the mode, mean, and most earlier, they should all be the same. The mode, mean, and median should all be the same value. If we looked at like the perfect normal distribution, the actual mathematical one that we use, this is true. The mode, the mean, and the median are all the same thing. It's like the perfect symmetrical distribution. How we're going to talk about it is pretty much these two values, the mean and standard deviation, the same mean and variance. The same way we were talking about them in like the start of the video when we were like learning about the things in the foundation section. We have our x values, our units that we're talking about, and we're going to have the shape of our distribution. It should be, in the normal one, perfectly symmetrical. That's the definition of the normal one. It is the perfect symmetrical usual distribution. And what we're going to have, the middle bit will be the mean. And you can see a kind of spread of the values. If I make this a little bit, I'll do that a little bit less fat than they were. We're going to see some spread of the values. But each way we're going to add or subtract one standard deviation. So to the right we'll have mu plus sigma, and then it's going to be mu plus 2 sigma, mu plus 3 sigma, and then same the other way, mu minus sigma, mu minus 2 sigma, mu minus 3 sigma. And it's just a measure of fatness again. How thick are we? How thick, boys? We need to figure out, are we thick or not? That is what that's measuring. And the standard deviation, the normal distribution, we've set it up so that we know how thick it is in terms of standard deviation. We have exactly, well, maybe not exactly, but like roughly 66% through there. I think it's 95 and then 99.7 or something like that. You're going to see different ones will say roughly different numbers, but they're kind of all correct. But this is coming down from that bit, this is coming down from that bit, and this is coming down from that bit. Yeah, that should obviously be like that. So symmetrical, everything's looking good. How are we going to use these then? Let's look at the CDF and PDF again. What the PDF is representing is if we take one of those distributions, binomial can be a different shape. Do you mean binomial is that sort of shape as well? Depends where your mean is, which way but depends where your probability is actually. The lower value will put it this way, higher value pushes it that way. Imagine that if it's 1, it's the perfect distribution of just like a line. Do you mean? You have to get all of your outcomes must be success. If it's 0, it's the perfect distribution of that way. There's one big line at this end. As we get closer to 0, to p being a half, it gets more symmetrical. So the PDF is going to find basically the chance of us being in this region. If you think about this being like, say, 7, this is the chance of us getting exactly 1, 7. So exactly the x. What's the chance of that thing? If we look at the PDF, we can have the same distribution, but now we're looking at not just, let me move that over. Yeah, we're not looking at just this number, but everything less than or equal to that number. Literally less than or equal to that number. We're adding up everything as we go. This is the same down here. It's still true for normal. Do you mean, again, this is definitions of just PDF and CDF. What are they doing? But notice we don't have any formulas here, so we're going to use the calculators every single time. Every one we don't have a formula for, so the CDF up here, and both the PDF and CDF down here, we'll use calculators. This is a calculator. And down here, we have both PDF and CDF are calculators. Calculate skills doing to get the values out for it. But it's effectively that. We want to take in our parameters, either the number of trials and probability, or the mean and variance. Could be standard, that depends which one you think of, doing the same sort of idea. Take in those parameters, take in the value that we've observed. What was our outcome? What outcome do we care about? We take those in, and the calculators give us the probability of that thing happening. Either of that thing happening with the PDFs, or something less than that thing, or that thing itself. So what's the chance of you getting like 10 heads out of 20? What's the chance of you getting up to and including 10 heads? So 0, 1, 2, blah, 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 9, 10. Hopefully, all making sense. Yeah, hopefully all making sense. Other bits then about the normal is going to be the standard normal. What do we mean by standard normal? We've just scaled it up. So the standard one, we have the mean of 0, standard deviation of 1. So everything's just centered on 0, and it's got the unit thickness. It's just like the average one you could have. Absolute average thing. Everything's going to be based on this. And then all the other ones that we deal with, like all the other normal types that you deal with, all the different parameters, are just transformations of that thing. You're going to add something to it to change the mean, slide it side to side, and we're going to multiply it to change the spread, change how thick it is. So this is actually very useful, and I'm going to talk a little bit about the standard one more than the other ones maybe, because we're going to use it to do the inverses. How do we go from having the probability and getting out the parameters? So I'm going to define, and you will see this written in other things as well, a few bits. We need to have phi of z. We also need z. We need to know what z is. Z is the transformation we do between the standard normal and the specific normal that we had over there. So z is going to be, like we always will have, z basically is distributed. So like capital Z is distributed normally that way, in the same way that like capital X is distributed here, but we look at the probability of all the little x's. So capital X is like the distribution name, lowercase x is the actual value. We did this distribution, what's the chance of us getting a 6? Here, Z is going to be the name of the standard normal. Lowercase z is going to be the actual probability of us getting, the actual value we get in that standard normal. What it refers to being then is a transformation. How do we go the other way round, or change between the two? We're going to take the distribution we had, subtract the mean, i.e. take it back to 0, do a transformation of f of x minus a, and then we're going to do a division by the standard deviation. So we're getting rid of our thickness. Divide by the thickness, taking it back to having a thickness of 1. Because what's this going to do? Yeah, shift it to the left by mu. Shift it back to where mu was. What's this going to do? It's going to stretch it by a scale factor of 1 over phi. So this is just a transformation that takes a distribution with 0 and 1 into 1 with mu and sigma. But using it is a little bit easier. So the function phi itself, what is that? Let's actually read all of these bits. You can go over there for a sec. You can come here. So z is that thing. Phi then It's just a fancy way of writing the probability. The cumulative distribution function, the CDF. It's a probability that that Z is less than or equal to Z. And the reason we want this, it's nice for the inverse stuff. So if we write down the inverse normal of whatever probability we get, this is going to look quite bad notationally, but it will make sense. So we will have the probability. This is just the prob we know. This is like the prob that we get given. We are given. Prob we get given. That will always give us some number. Do you mean just some number? But it's going to be equal to the thing that we've just been talking about. X minus mu over sigma. Where this X is going to be like the value that we're given. So you might be told, oh, I did 10 coin flips. Or let's say that's normal distribution here, isn't it? So let's say that we had the heights of people. And we're looking at people that are 5 foot tall. This would be 5 foot, would be 5. This then, the probability of us being less than or equal to 5 foot tall. So it's going to be like 10% or maybe less than that. And what we'd see, we just get some formula. This you get from the calculator. It's just going to give you some number. They give you this number. You put it in the calculator, it gives you a number back. They give you this number. And from there, you can set up simultaneous equations. So for example, you'll get out the probability. You'll get out, sorry, the inverse phi of like, say, 0.1. And you'll know that then is equal to, say we did 5 foot. And we're going to have, it's going to be take away mu over sigma. We can then do a similar thing where this was now actually, let's say it's going to be 2. And that is going to be equal to, we could have 6 minus mu over sigma. And now the two green ones together, two equations, two unknowns, we can solve them for phi and sigma. So just to note, these bits were inverse phi. Let's do them in blue. What does inverse phi actually measure? It is the spread in terms of standard deviations. So if we get a number out, like here I've done 0.1, what that means is that we're 0.1 away, 0.1 standard deviations away from the mean. Here we were 2 standard deviations away from the mean. That's what this measure is. Number of standard deviations from the mean. That's the Z. Do you mean that's the Z score? So this inverse like gives you a Z back. Do you mean this is equal to Z effectively? So like this, you can see that thing was Z, wouldn't it? So Z itself is, yeah, number of standard deviations from the mean. Number of sigma from the mean. Is there anything else in distributions? Yes, there is. The continuity stuff. Can I squeeze some bits to fit it on one page? I think I can. Let's move you up. Let's move you up a little bit. Let's move all of this stuff up as well. So the continuity corrections, what's that about? Well, it's about continuous and it's about discrete variables. And the idea that basically, if you think about the formula we have down there for the PDF of the binomial stuff, inside here, what is this thing? N choose x. It's that n factorial over, or in this case, x factorial over n minus x factorial. Say we do 1,000 trials. N factorial, very, very big, isn't it? Too big for my little calculator to deal with. Probably too big for yours. So that's an issue. We want our calculators to do the things we need them to do. We don't want our numbers to become so large we can't deal with it. So the continuity correction, I'm hoping this will fit in here. Let's try and squeeze some more bits up a little bit. It's basically a way that we can take a binomial distribution and approximate it as a normal. So it is part of the normal, but I'll do its own little section down here. So the continuity correction, cont in u it t correction. It's called that because we're taking something that is discrete. Binomials are discrete ones, yeah? We can only get certain outcomes. If I flip a coin 10 times, I can get 0, 1, 2, 3, 4, blah, 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 up to 10. The normal, these are continuous. I can get any value out when I measure the height, as long as I'm able to measure accurately enough. But that the limitation isn't in the maths or the system, it's in my actual physical measurement. And in maths, we don't care about just because your ruler isn't good enough, our maths is good enough, your rulers need to catch up and get as good as our maths is. Here, we're doing that basically, saying we have discrete things, these are continuous. So when we look at something discrete, what's the chance of getting a probability of, like, say, getting 5? In the continuous, that's anywhere from 4.5 to 5.5. That's what we're doing here. We're effectively taking the number line of just like whole numbers and seeing what numbers round to them. So you might have the number 5 and then the number 6, and we'll do the number 4 as well over there. What we're going to see is having little barriers at these bits, which are, like in this case, 3.5, 4.5, 5.5, and 6.5. And we're going to work with them then to figure out which group we need to be. So effectively, we could write down lots of formulas. There's lots of them here. This is what I do to figure out if I am unsure. Say we had the probability that x is greater than or equal to 6 when we're dealing with something binomially. How do we turn that into something that's normal? Let's look at the number line. We have the number 6, 5, and 7. So just doing the number line. The lines then represent, like I said, 4.5, 5.5, 6.5, and we would have a 7.5 over there, yeah. On the top row, thinking about binomial, bigger than or equal to 6. Where gets a tick? This does, and this does, but this one doesn't. So when we start thinking about it normally, we want to go from this line to be continuous. So it's going to be bigger than 5.5. So x will be bigger than 5.5. Just to note, there is, you can do the equals. It doesn't make a difference. The idea being that we can never be exactly any of these numbers. How tall are you? We can always zoom in. We can always get more detailed. So like the PDF, in theory, wherever it is, the PDF of the normal is kind of just always equal to 0, because you can never be exactly a certain height or exactly a certain distance or exactly a certain time. You've always rounded at some point, so you've lost it. And this is what we're doing here, is trying to see, oh, imagine we had rounded. Imagine you flip the coins, and where we go? We'd flip the coins and you could have got like a half of a heads or a 2/3 of a heads. We're going down and saying, well, if we round everything, what numbers are going to be? This is then doing the reverse. Like, what is the rounding that would have given us this discrete thing? Is that all good? Is that all good? Is that all good? I think it is. So the last and the most dreaded chapter of all, the hypothesis test. What are hypothesis tests? You are just simply calling out absolute bullshit. Yeah? Someone's made a claim. My coin is fair. The chance of it being a heads is 50%. Lovely, good claim. Let's see your data. Oh, you flipped it 10 times and you got 9 heads. Bullshit. Your coin is not fair. You're chatting out your ass. That's what we're trying to do. Either someone's made a claim or a claim has already existed that's already proven to be true or assumed to be true. And we're going to come in, look at what's actually happened and be like, you know what, mate? Nah, you're chatting out your ass. I'm not believing you anymore. I'm going to change my mind. Important thing to notice, we're just calling the bullshit on him. We're not making a claim that we are correct in our new thought. So we can only talk about H0 at the end. Only talk on H0, i.e. like we either accept, let's stop doing capitals now. Either we accept H0 or we reject it. We never accept H1. We haven't proved anything true. We're just calling bullshit, trying to prove people wrong or say, oh, you know what? I can't see that that's wrong. Do you mean like what we've seen is actually, yeah, you know what? Maybe you're talking sense. Where is our kind of bullshit meter? When is it going off? That is going to be the significance level. So the significance level, the sig level, is our bullshit meter, or our bullshit threshold. Do you know what I mean? How much bullshit can we take? What is the most unlikely thing that we would allow to be not bullshit? Do you know what I mean? So if we have a level of 5%, then what we're saying, any observation that we make, that if we just randomly did it loads and loads and loads of times, if we randomly made the same experiment 1,000,000 times, we would expect to see this thing 5% of the time. And we're going to say anything that would be less likely than 5%, that's too obscure for us. That's too much bullshit there. No, that didn't happen. So going back to the coin flip example, if we flip it 10 times and we get 9 heads, that's what, I don't know what the chance of that is, but it's very low, isn't it? It's a very low probability of doing that. It's too low. The thing that we saw was too unlikely compared to what our threshold is. We're allowed to have 5%, anything less than that, nope. We think that we are going to reject H0. Anything more than that, we are going to accept it. That is effectively what hypothesis testing is. Some terminology then, just to talk about it. We have the sig level. You might see a P level sometimes, or the actual sig level. This is the kind of minimum one that would result in the same outcome. So it's the min with same result. You'll see in a second, it's basically the probability of the tails actually being, or the probability of the critical region. Do you know what I mean? Actually being in the critical region. What else things do we have? That's that one, that's that one. Yeah, the tails then and the critical regions, critical values. So yeah, critical regions for the best way to talk about it. The critical region, this is the set of outcomes that cause rejection. This is the set of bullshit. Set of bullshit that cause rejection. So when we flip that coin 10 times, what results are going to trigger our bullshit meter in our head? If I get 0 or 1, yeah, bullshit. If I get 9 or 10, bullshit. 7, 8, 8's a bit on the edge, isn't it? That's when it comes down to this. To say, oh, okay, how unlikely is it? How do we decide what's bullshit and what's not? Because all this is bullshit. This tells us how much bullshit we're allowed. So this is good. The critical values, just to note down, so critical values, they're the least extreme of the critical region. Least extreme. Let's look at a graph then. Let's get our distribution and plot some of these bits on there. So we've got that, we've got this. We're going to have, we'll look at two tailed, but one tail is fine, like for our diagram here for a second. So all of the red bit, these are the critical regions. Critical regions. The critical values then are the first ones in there. Do you know what I mean? As you're stood here and you walk along, first one you see. Walk along, first one you see. But it's inside the critical region. A critical value is in the critical region. I'd call the other like boundary values. If you think about like the last one you see before you get to the region, I'd always think about them as being kind of boundary values. And then yeah, I don't think you ever have given them a name, but it's like the very edge of the acceptable zone. So this is the way to think about it. Critical region is going to be reject, and the non-critical region is going to be the accept. So this is going to be accept H0, and then the outside bits are reject H0. What is H0? What is H1? H0, like I said, was the original thought. So this is the null hypothesis. Again, just names of these, doing what we thought originally. If we do underneath, H1 is the alternate. So it's like a new idea. You might see alternative as well. Same thing in it. Different idea, something new that we think about that might not be the same as what was already thought. So that's the basics of what we want to do. How are we going to do it then? Two different ways, really, kind of three, but it's really only 2.5. Either we are given a test statistic. Test statistic. What is that? It's an observation. I.e., we got 9 heads from 10 flips. we observed something actually happen, and we're going to use that then to see where on this diagram we were. We would want to find the probability of our observation, or it being more extreme. So in this case, it would be 9 or 10. So it's the probability of this outcome or the more extreme ones. So i.e., yeah, probability of x is greater than or equal to 9 if we do 10 flips. And what we need to think about is that bigger than the significance level. If what we see is more likely than the significance level, then that tells us that the thing wasn't actually that obscure. There's not that much bullshit there. So we do not reject H0. Other way around then, if what we saw it was so unlikely, so much less than our bullshit threshold, we are going to reject H0. Maybe we should go up and say that we don't ever accept H0, we just don't reject it. It's probably a better way. Do not reject. Yeah, we never really accept. That's the way to think about it. It's already been accepted to be true. We're not going to reject it in this way. So not reject. Don't reject. There's insufficient evidence to reject. It's the phrase I use at the end. That looks good, I think, for like the general idea of it. Oh, the two-tailed and one-tail. When we get given our null hypothesis, what we generally see is either two cases. Either we have it like, oh, the probability is less than, say, 0.3. Or we could have that the mean is more than 4. This would be for one-tailed. Sorry, these are going to be the H1. One-tailed. We're looking at different directions. We're assuming the probability is actually less than this. We're assuming the mean is actually more than this. Like, this is our assumption, like, not our assumption, but our like bullshit thing. Do you know what I mean? Our like new alternate hypothesis. We're thinking our coin was fair, but we showed that we had like our observation was 9 out of 10, 9 heads out of 10. So we think that the probability is more than 0.5. We have a direction in which to aim our discovery, our investigation. So that means that we would only have one of these tails. This one, there would be no critical values, because the way that we're trying to prove the null hypothesis wrong is in a certain direction. So we're not interested in that way at all. We're only interested in the way that actually could possibly change our mind. But there could be certain cases where you don't know. You might just think it's different. So for the two-tailed, we will simply see that it's not equal to some number, say a half, the thing we were saying about. So just not equal to, compared to these being directional. Anything else I can think of? Oh, the means. I should really talk about this back here actually for the normal, but it kind of comes up just in this bit. So we will mention it here. We'll put it in this little bit. So this is talking about like we've done just one experiment, yeah, one sample. What if we do a sample of samples and we look at kind of the sample mean, like the mean of the samples? We can get a new distribution where the mean will be the same, but the standard deviation gets, the variance, gets divided by how many there are. Thinking about this, if we do, basically this is saying that we're going to do this same distribution n different times. So the actual spread of the data gets a bit thinner. The more times you do things, the more that we kind of converge on that average value, because it's the average. I mean, that's the definition of it. We're just going to get closer and closer to that thing. So we're saying that if we do it twice, that thickness gets halved. If we do it 10 times, that thickness gets 1/10, get decimated. So this is called the sample mean, because it's the mean of the samples. Sample. It's a bit weird with the wording. Do you know what I mean? Maybe sample mean is probably not a good way to think about it. It's the mean of samples. You're doing multiple experiments, multiple surveys, multiple samples, multiple censuses, and you're looking then at the results across many of them. because we're going to use that with the hypothesis test in a second to talk about that kind of mean of like the sample means. So that's good. I think that's everything from that little bit. We'll talk about actually doing the I'll do some quick examples on hypothesis tests because we do them on correlation as well and like how they work. It's not such a bad way to think about it. So yeah, let's do a hypothesis test. We'll do the fair coin one, do you know what I mean? And we'll do the whole thing and we'll talk about how to define a critical region. So yeah, this is going to be a hypothesis test. So it's a hype test. That's it. You're testing the hype, Jim. Testing the hype test. So let's have we'll do 10 coin flips. So 10 coin flips. What's our assumption? What's our null hypothesis? What I'm going to do, this is all I'd write in the exam on the right hand side. So this is the actual exam, like what I would write. Exam answer. Our H0, the probability was a half. Our alternate hypothesis, let's say we didn't know which way they were going for. What we're going to do is we'll work out a critical region here, and then we will look what would happen if you had a test statistic. You can look at both sides of it. So we want to go basically and try and find every value that would change our mind. To do that, we would need to be given a significance level. So let's have 5%. What we have is two-tailed because of this one. So this is actually going to be split into 2.5%. One at either end. But yeah, each bit is 2.5%. So just taking that 5%, splitting it into. Anything else we need? Don't think so. Now actually to go through and find it, we have our, so it's going to be binomial, yeah? I'll probably write down actually that it's going to be x is distributed binomially with a mean of the 10 that we found and a probability of a half that we are assuming is true still. We are not yet to actually call out the bullshit, so we have to believe the bullshit until you can prove it wrong. Not in the real world, but in maths you do. So how do we want to do this? It's kind of a bit of trial and error actually to get the critical values. What we want to do really is find the first numbers here. So I'm going to go through and with a calculator, I'm going to find what's the chance of us being bigger than some number or more extreme. Let's make a guess that it's going to be 9, yeah? This is just a guess. I don't know right now. When I use those calculators, like you'll have them on your actual calculator. I don't have one of those because I don't need one, but I can get an online one. Do I have them here? I have them here. Hold on. Let's bring it out. Yeah, let's do that. Put you over there. Yeah, look at this. Look at this. What's that? Technologia. So now, what do we have? Probability of success was 0.5. 0.5. Number of trials. We flip that bad boy 10 times. We care about 9 right now. Let's calculate. We wanted to get the greater than or equal to. Your calculator might have to do some flipping around for this. Maybe I'll speak about that in a second. But you can see from the 5th kind of grayed out number there, the greater than or equal to, we get a number of 0.01075. I'm going to do the same thing now. So this is less than 1%, yeah? So what that tells us, we know this whole blue region is 2.5. So somewhere in there is the 9. We don't know whether 8's in there yet. So let's go and check 8. What do we get? We'll change this number to a 9. From a 9 to a show keyboard. Oh, why has it done this again? Change it from a, that's not too bad actually. Change it from a 9 to an 8. What do we get now? 5 down there. 0.05469. And the important thing is that 0.025 is in there, i.e. 2.5% is in between these two numbers. So when we go and look, I'm going to draw a new distribution for it. We want to find these regions, and we've basically spotted at the upper end that 9 is there, but 8 is there. So the first critical value on the upper end is 9. The only critical value on the upper end is 9. But the critical region starts at 9. It includes 10 on that end as well. Same thing the other way around then. We want to do like the symmetrical version of this. where this is a half, it will, look, we started off with a half, it's going to be symmetrical. So we should have seen, like, if we do x is less than or equal to 1 and less than or equal to 2, I think we get exactly the same numbers. Let's just double check. I'm not being silly. Get rid of u, put a 1, and I get, I think we want to be less than or equal to now. We want to be more extreme. We want to be further away from the mean. Less than or equal to 1, we got 1074. So that's just, yeah, rounding thing there. It's only symmetrical because of the half. If we had a different number, these would not be symmetrical. So you might have to trial and error, but you want the same idea of getting 2.5 between the numbers that we have down here. So less than or equal to 2 was, again, that 5 number. 0 first. 0, 5, 4, 6, 9. So again, 2.5 in between. Because ideally, yeah, really look, this is less than like 2.5%. 2.5%. This is more than 2.5%, less than 2.5%, more than 2.5%. So we found that we have 1 over there, 2 over there. So what is our critical region? It's either, what we can do is just a set, it's 0 or 1, or 9 or 10. You could do, I suppose, like the x is greater than, x is an element of the real numbers, do you know what I mean? But this should be fine. When we actually, like, you don't need to do that when you just listed everything in the set, do you know what I mean? Just a list of everything in there. You can obviously write this down as it's like x is less than or equal to 1 or greater than or equal to 9. Do you know what I mean? They might want you to do it in set notation, but either way, whatever numbers are going to be causing us to call out bullshit. So what we have then, say we had a test statistic of 8. Our observation, we got 8 heads out of 10. 8 is not in our critical region. Let's do that symbol a bit neater. It's not in our critical region. So that tells us there's not sufficient evidence to reject H0. We haven't seen enough bullshit to reject the bullshit. Or at least the thing we did see wasn't enough bullshit. It wasn't bullshit enough. It's quite actually probable of happening. There's a 5.4% chance it did happen, 5.5% chance it happened, and our threshold for bullshit was 2.5%. That's it. You can see I've talked a lot here. What things are actually written down, that's pretty straightforward, isn't it? That's pretty straightforward. Use your calculator to get these numbers. See what they are. Either then, though, it might just be asking that, might be the answer. Do you mean? Generally, it's like one of these two versions you do. But at the end, like, we'll do that. But yeah, you find the critical region, or you're going to test statistic. If you're given a test statistic, you just do one of these rows, do you mean? So like if we were just given that straight away without this stuff, we'd have done the 8, got that it's bigger than 2.5%, so that there's not sufficient evidence to reject. That's it. That's all we've got to do. How is this different with binomial, with normal, and with correlation? It's just the way that we get this part of it. Which calculator are you using? Are you using the binomial one? Are we going to go over instead and use like a normal one instead? And you do the same idea, just being careful about making sure you put the right way round on these bits. Only other bit then would be the correlation. Exactly the same though. Where these numbers come from is just going to be in the formula book. Somewhere. There it is. So we can see a few bits. We don't do the Spearman anymore, I don't think. It's just the product moment coefficient. They'll give you some sample size, because when you've done like the correlation thing, they've done some sample and they're finding the correlation between that sample. So you'll be told the sample size that you have. All we want to do, go to that row. Ooh, so let's try and do it. I'll do it at the very bottom. Oh, it's going to be in the way, isn't it? Can we see that? Maybe. Let's do it above that line. So we've got row 20, say. And we're told then the significance level, that's going to be the column. So we go down and look at it just for that column and pick off what number it's going to be. So you get like the y coordinate of it, do you mean what row we're in from the sample size? And then we get the x coordinate from the actual alpha they've given us, the significance level. Sometimes they used to give you like it had both bits on. I think there was something else on there. You'd have like a, what do you call it? Where's it gone? Like the one-tailed, two-tailed bits, it appears to be they've got rid of that. And look at the top, what does it say? One-tailed test. One-tailed test. So, yeah, that should be pretty much everything, I think. Let me have a little double check. In two-tailed, what's going to happen here is you'd get half as much. I'm pretty sure. Let me double check. Yeah, they used to have it on here. Like, it would be in there that you got different, like, you had different rows on the top for that. Do you mean? Let me just double check. That's why I was thinking it would be in there, so I didn't need to double check beforehand. Do you mean? Two-tailed height. Oh no, two-tailed PMCC values. Let's see what pops up. Do they have it? I think they have it. I want just a image. Let's see. Give me one sec. Two-tailed, one-tailed. Yeah, the two-tail is double. Two-tail is double. So on this correlation coefficient thing, where you have one tail there, that's the correct one for that row at the top. If you were trying to do the two-tailed test, so you would need to look at the half row. So let's just clarify that. Like if we have one-tailed and 5%, then that's going to be column 2. If it is two-tailed and 5%, that's like the same. It's exactly, yeah, it's equal to having its one-tailed and 10%. No, 2.5%. 2.5%, other way around. Yeah, we go smaller. Because, yeah, think about it. Two tails, 5%. One tail, get 2.5, don't you? Yeah, lovely. Simple. Sorry, little faff up in my head there. Yeah, that's a weird thing they've taken out. See where the numbers are for level, like 0.1, 0.05. Used to be 2 rows, there's one with each one. Maybe that will still be an exam, but it doesn't look like it from this. Is there anything else? I don't think so. Oh, maybe, well, one thing. Let's look at, like, if you did need to do the rearrangement. Say your calculator can't do the other sides. What do we do is make sure that you count every number. So if we need to have the probability of x is less than or equal to a, that's 1 minus. Well, we've already counted a on the left, yeah? Obviously, I'm going the other way. I want to be bigger than now. But I don't need to count a. A is counted on the left. So a is only on one side. These two bits, they must represent every number. They must be every single number. Represent every single number. Lovely jubbly. I think that is everything. This obviously works well. You can move these around, do whatever you mean, but as long as they all represent every single number, you can think about it the other way around. Add that to the left. What do we get? Probably that x is less than or equal to a, plus probably that it's greater than a is 1, because either you are a potato or you're not a potato. There are no other options. So what have we done? I think we finished it. Sampling, nice, straightforward. Learn the bits, learn the different types, how you do them, and reasons why, but they should be kind of common sense. Integer stats, this stuff you should know, like these main bits, like these definitions and stuff, like you should have known this from GCSE. Maybe double check that bit, make sure you can do the actual interpolation to find out where the medians are. Understanding this idea, if I double every value, it doubles the mean. If I add 10 to the values, it adds 10 to the mean. If I add 10 to the values, it doesn't change the spread, it's just moving it around. But if I scale the values, I also scale the spread. And remembering that here we're talking about the spread of squares, so it squares it. Here it's the spread of linear things, so it's linear. Weirdos, kick out the weirdos, do some graphs, do you know what I mean? You got a good cum freak, good bit of history. So this is all, but yeah, about the area. Always be careful in the area, remember that formula. Correlation, you doing the same thing or not? You doing what I'm doing? Yep, we're doing the same thing. Yep, we're doing the same thing. No, tell a lie. We're doing the same thing, we're doing the opposite thing. we're doing the same thing, and we're pretty much doing exactly the same thing. Doing the same thing, but it's a little bit varied. Different thing, a little bit varied. Different thing, very different. Ooh, fuck knows. No idea what's going on there. If it's exponentials, get rid of exponentials, make things into straight lines. Straight lines are easy. Curvy lines are not so easy. Everything in maths basically comes down to, can we turn it to straight lines and then understand them? Really. Probability. Learn all the definitions, like know what these words are, just so they don't faff you up. These bits are the main bits though, like how mutually exclusive, intersection is 0. Exhaustive, union is 1. If it's both, this is going to be true. We have the idea of intersection and union, dealing with those bits, hopefully not too bad. Tree diagrams, conditional probability going through, thinking, okay, what's the chance of this? Like, if we are at this state, how do we get to this next one? Not just in general, just to pick a blue one, but after we've got to this journey already, how do we move to the next one? Independence, chance of this happening isn't affected by the other thing happening, and you end up in a situation where either both are true or neither's true, so you can prove one by proving the other one, or vice versa. If one's given to you, you know this one is true too. This stuff, nice and simple, GCSE again. Distributions, every single outcome has a probability. Binomial, 2 outcomes. Fixed number of trials, independent outcomes, fixed probability. We're going to look at like the number of successes, number of failures, probability of getting a certain amount of successes, probability of getting up to and including that number of successes. Things can be normally distributed, so just like the natural distribution of things. Talk about the mean of it, standard deviation, and then the standard normal, so mean of 0, standard of 1, and then using that stuff, the inverses. Have I moved? I did move. Moved very far. Yeah, using the inverse stuff to actually form simultaneous equations where we're going to solve for mu and sigma. You might be given one of them and you just need to solve for one value, do you mean? But you'll be given, like, yeah, probability that x is less than or equal to 5 is some number. Take that number, work out the inverse standard normal, plug in these equations. Continuity correction, rounding but in reverse, do you mean? Undo the rounding. And then we're calling the bullshit on hype tests. Hopefully this makes a bit more sense. So you're basically seeing what we observed. How likely was that thing? Oh, it was a 4% chance of happening. Our threshold was 5%. We've observed 4%. That's too unlikely. I'm calling bullshit. We're going to reject your claim. If what we saw, however, was quite likely, it was 9% chance of happening. Oh, you know what? Yeah, I could see that happening. I can get 8 heads in a row. That's okay. Or 8 heads out of 10. That's fine. That's acceptable. I think that's okay. That's it. Good luck.